Hello, everyone. Today we're going to talk a little bit about modular arithmetics. And everything that we're going to be talking about in modular arithmetics, we're going to be just explaining just the fundamental concepts behind modular arithmetics. And we're also going to dive deeper into actually solving some questions with modular arithmetics. Without further ado, let's begin. All right. So, modular arithmetics is a system of arithmetic for integers where numbers wrap around a certain value called a modulus, or which is called m there. So let's just say if we write a mod m is equal to r, right? This means that when a is divided by m, the remainder of the division of the two is r, right? So just a visual representation here. I know I'm going to say something there. So let's just say we have 2. Okay, no, not 2. 3 divided by 2, right? So 3 divided by 2 normally is 1. Okay? Yeah, 3 divided by 2 normally is 1. But then there is a remainder here within this function here, which is a remainder of 1. That is, when you say 2, right, times 1, our function there, 2 times 1, meaning if you multiply these two together, if you multiply these two together, 2 and 1, you get 2, right? Then the answer that you get, you add 1, which is basically going to be 3, which is this guy here. So you see how this actually works out, right? So a mod m is equals to r. So this means that when a, which is this guy here, 3, is divided by m, the remainder is r. So a basic example of a modular operation is find 17 mod 5, right? So the solution would be 17 divided by 5 is equals to 3 because 15 times 3 is equal to, oh sorry, not 15 times 3, sorry, 5, yes. Let me get my pen. So 5 times 3, so 5 times 3 is equal to 15. And then when you see that 17 there, when you subtract that guy, you get a value of 2, right? So the remainder of 17 divided by 5 is going to be 2, but 17 divided by 5 naturally is 3, right? But then the remainder being 2. So we see that 17 mod 5 is equal to 2. I hope that kind of solidifies the understanding of basic modular operations. Let's try another one. Negative modulo, right? So find negative 8 mod 3. Oh, it's the same concept here, right? Where we say negative 8 divided by 3 is essentially negative 2. Because if we remove the negative value, we say 8 divided by 3 is practically 2, right? Because when you multiply 3 times 2, that's going to give us 6. But then the remainder of 8 divided by 3 is 2. And when you add 6 and 2, you get 8. So we get the primary function there, okay? So here it's the same as the opposites, like that there. So we have that. Okay, so that's just basic understanding of everything. I know the example that I used was using positive integers, but it was just to help you understand in greater detail what exactly is happening, okay? So 8 divided by 3 is negative 2, remainder 2, right? Thus, negative 8 mod 3 is 2. So what we are getting here, or what mod is interested in, is the remainder here. So we've got a, and then we've got m, right? A mod m is equal to our remainder here. Not the answer, but the remainder of the answer. I hope that makes sense. Okay, so now let's go to some basic mathematical rules that govern modular arithmetics. So we've got addition here, where you have a plus b mod m. Now this can be further expanded, where we say a mod m plus b mod m multiplied by mod m. Okay, so the modular function of this guy plus the modular of this guy multiplied by, or not necessarily multiplied by, sorry for that. We get the mod of this guy, we also get the mod of this guy, and then we find the overall mod m. Okay, for now it might look like it's gibberish and whatnot, but stay with me. I'm cooking, sorry. Yeah, so here we have a mod m, and then we've got b mod m there, which is m mod m. So multiplication is the same concept, just that we're multiplying instead of adding. Then for exponentiation, we've got a the power b mod m, which is the same as a mod m the power b mod m. So these are going to be very important later on in what we're going to be doing next on. And also this is also important for RSA cryptography and encryption. So yeah, that's going to be something. Okay, so let's go to our third example, which is modular addition, using the same rules that we defined earlier. So we've got find 12 plus 9 mod 5. Here we say a plus b mod m, right? So we're trying to get this guy. So find 12 plus 9 mod 5. Well, the simple solution here is to say that you just add these two, right? Or you could just say 12 mod 5, right? Plus, what's this? 9 mod 5. Then the overall function that you add there, you add, or you do it mod 5. But the simplest way is to just say 12 plus 9 mod 5, which is 12 plus 9, which is 21. And then you say 21 mod 5, which is 1. Now, 21 mod 5 is actually 21 divided by 5. And we know that the answer here is 4, right? Because 4 times 5 is equals to 20. But then there is the remainder of 1. This is the one we're talking about. So 21 mod 5 is equal to 1. Okay, so that's the function here, modulo 12 plus 9 mod 5 is equal to 1. Hope that makes sense. It's clear and simple enough. Okay, let's go to a concept called the greatest common divisor, right? In secondary, you had fractions, right? Fractions had kind of like this orientation here, where you've got a particular number there, maybe 2, maybe 4 there, and then we have like which one are we going to use, or the lowest common factor, right? Which we put 2 there. So 2, and we've got a maybe there somewhere there. We've got a and we've got b. Then we are multiplying or subtracting or whatever, right? What would particularly do is we would get the lowest common factor, right? And then we'll make it our primary denominator. And we make it our primary denominator there. And then we multiply this guy there. What I'm trying to say is that that was for the lowest common factor. Now here we've got the greatest common divisor, okay? So the greatest common divisor between, let's just say, function A and also function B would, in this case, be 4, right? So that would be our greatest common divisor between this guy and this guy. So let's just say we have A and we have B, right? And these guys are factors of each other, okay? Oh yeah, they're factors of each other. Let's just say 120, right? Oh no, not 120. 140. Yeah, 140. Like that. So the greatest common divisor between 140 is basically 20. Right? Because 20 can enter into 40 without leaving a remainder. 20 can also enter into 100 without leaving a remainder as well, right? But then 2 can also enter into 40, 2 can also enter into 100, 5 can enter 40, 5 can enter 100, 4 can enter 40, 4 can enter 100 as well. What else? 10 can enter 40, 10 can enter 100 as well, right? But we're looking for the greatest common divisor, which is 20 between these two variables. So you can even have 31 and also 25, right? The greatest common divisor between these two is 1, because there is no number that can enter 51 and also enter 25 without leaving a remainder, right? Apart from 1. So 1 in this case is our greatest common divisor. So at least you have an understanding of what a greatest common divisor is, right? So with that being said, the greatest common divisor of two numbers is the largest positive integer that divides both numbers without leaving a remainder. Okay, so this uses two methods. So using prime factorization, something like what we've done here, and the Euclidean algorithm. So we're going to look into both of these in just a moment. So prime factorization, basically here we've got GCD, which is 36 and 48, right? So what we're doing here is that we're going to break down these numbers into their primary factors, and then now we're going to see which ones are common. So here we've got 36, which can also be represented as 4 times 9, right? So 4 times 9 gives us 36, but then 4 times 9 can also be further broken down into 2 squared multiplied by 3 squared, okay? We can leave that there. And then we've got 48. 48 can also be represented as 16 times 3, which can also be represented as 2 squared times 2 squared times 3 to the power 1, like that there. So the common factors between these two numbers here could be that we've got 2 squared there, we also have 2 squared there, so they are common. And then we also have 3. Okay. Hold up. I think there's an error somewhere here. So the common factors between, oh yes, 3 squared. So 3 squared can also be represented, yeah, this is correct. So 3 squared can also be represented as 3 to the power 1 times 3 to the power 1, like that there. So you can feel free to actually break this down as well. So here you see that you got 3 to the power 1 there, and you also have 3 to the power 1 there. Okay, so you've got these common factors, which is 2 squared times 3 to the power 1. And since these are your common factors, what you do now is you get these two common factors and multiply them together. So meaning the greatest common divisor of both 36 and 48 is going to be 2 squared multiplied by 3. And 2 squared is equal to 4, and 3 to the power 1 is equal to 3, and 4 times 3 is equal to 12. So here we see that the greatest common divisor between 36 and 48 is 12. Okay, 2 can enter into 36, 2 can also enter into 48. Yeah, 6 can enter into 36, 6 can enter into 48 as well. But then the greatest common divisor using the prime factorization method is 12, because we're looking for the largest positive integer that we can use to do that. Okay, I hope that makes sense. Okay, so now let's look a little bit into the Euclidean algorithm. And the Euclidean algorithm basically just takes a different approach in understanding these guys. Yeah, I think there's a problem somewhere here. Okay, sorry for that. Okay, so the Euclidean algorithm basically has got a set of rules, and it's different from the way the prime factorization method works. So here we say that if a, for some value of some positive integer a, is greater than b, then the GCD between a and b is equal to the GCD between b mod b, a mod b. Okay, so you repeat this whole process until b is equal to 0. Then the GCD, then a is the GCD. I know that this is a a little bit confusing, right? I'm sure you're like, what is it saying? What is it talking about? This does not make any sense. So let's try to use an example here, right? So find the greatest common the divisor of 48 and 18 using the Euclidean algorithm. So here we say that 48 mod 18 is equal to 12, right? Because if I get my calculator there, let me just say this. I'm with my calculator here. So 48 divided by 18. So 48 divided by 18 is equal to 2.6 dot 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 dot. Yeah. So we see that there, right? But then what happens now is that if we multiply 18 times 2, 36. 36, 48, let me just say this, 48 minus 36. This gives us what? 12, which is this guy here. You seen that, right? So we get 48 mod 18, which is 2, remainder 12, right? And then what we do now is we get this value here, 12, and we put it as our new mod there. Okay, this is what we repeat now. So we get 18, we push it there. Basically, we're kind of like pushing like that. So we say 18 mod 12, okay? It goes in there 1, and then remainder of 6, which is this guy. And then we push that there, and then we push 12 like that. And then we say 12 mod 6 is equal to 0, right? So here, repeat until B is equal to 0, then A is a GCD. So repeat until B is equal to 0, right? Then A in this case here is this guy. This is B, okay? Yeah. So repeat this whole process until B is equal to 0, then A is the GCD, okay? So this is basically how you go about it. Now, I'm sure you're wondering, say that, no, there's B here, there's A and everything. So those are just the rules and the conventions behind it, right? But the order of operations is that you've got 12, or you've got this guy here, right? You first find the mod, then you push this guy here, then you also, what's this one? You push this guy here, you push that guy there, and then you find the mod of those two, right? Then you push this guy there, push that guy there, and then that's the mod. Until you reach a value that is 0, right? So until you reach 0, that's when you'll be able to actually like get your greatest common divisor. Yeah, so that's using the Euclidean algorithm, okay? So if you want to represent this using pseudocode, this is that guy. So while B is not equal to 0, place B in a temporary array, right? Then you say that A mod B is assigned B, and then the temp variable, which is B now, is assigned to A. So you continue, so on and so forth, but he's not going to bring this. This is just a visual representation of how it's supposed to look like, right? Cool. So now, here we have modular exponentiation. So we talked about this guy here. We talked about multiplication. We also talked about addition, but we also talked about exponentiation as well. And we also talked about the Euclidean algorithm and prime factorization using the GCD. But then all this is actually leading to something that we like to call RSA encryption, which is cryptography. So modular exponentiation, which is known as fast power, is used in cryptography, right? It computes large numbers efficiently using modulus. So for an example here, we have compute 3 to the power 10 mod 7. So instead of computing 3 to the power 10, which is equal to 59,049, and then finding the mod 7 of 59,049, we see that it's going to take us a long time, right? So we can use modular exponentiation and say that 3 to the power 10 mod 7 is equal to this particular function here. Let me go back to this. Let me go back to this guy. So we've got a to the power b mod m, right? So a to the power b mod m is basically expanded to say a mod m to the power b mod m, right? So this is what we're going to use for modular exponentiation. So 3 to the power 10 mod 7 is equal to, here we're going to divide this by 2, or basically we're just going to separate it by 2. Okay, and I'm pretty sure you have seen here, you've noticed that here we've got a mod m b, right? So this b is multiplying this m there. Okay, so it's the same that's happening here. So we've got mod 7 there. So we've got 7 and we've got 7. And then the b is multiplying both sides here. So if we wanted, we could have just said, for simplicity, we could have just said 3 mod 7 to the power 10, right? But then that's going to be a huge number or whatnot and everything. You can choose that if you've got time to compute that, but we have 3 to the power 5 mod 7. And then once you solve this, then you square that number and then you modularize this function as well. So let's just try to compute this. Let's see if I've computed it. Let's try to compute this. Where's my calculator? Okay, so let's try to compute this. I've got my calculator here. So 3 to the power 5 is essentially, so 3 to the power 5 is 243. 243, right? Mod 7. And you can try to find out this number here. You can just say, how are we doing this? 243 divided by 7, which is going to be 34, right? Which is going to be equal to 34. Oh, let's just say this guy, 243 divided by 7, which is 34, right? Then 34 times 7. 34 times 7 is 238. So we say 243 times, minus 238. Okay, so we have 243 minus 248. 238, which is 5. Oh, we can put that there. So this function here primarily is 5. Okay, so now remember this guy is wrapped within these parentheses. So we'll just say 5 squared mod 7. So 5 squared mod 7. And 5 squared is basically 25. Right? So 25 divided by 7 is 3. Right? Or basically just to say 21 divided by 21 minus 5 is 4. Right? Because here 5 squared is 25, and then 7 enters into 25 3 times with a remainder of 4, because 7 times 3 is 21. 21 minus 5 is 4, right? So here we've got a modulo of 4. So the overall function of this 3 to the power 10 mod 7 is 4. I hope that makes sense. Okay, so this is the pseudocode, and again, you're not going to be asked to write the algorithm. It's just nice to know if you get the algorithm here and whatnot and see how it works. Okay, so with that being said, the final summary here is that modular arithmetic basically deals with remainder operations, and it follows addition, multiplication, and exponential rules. And the greatest common divisor is basically the largest common factor between two numbers. The Euclidean algorithm is the most efficient way to find it, even though you can use the prime method. The Euclidean algorithm is the best one to use. So you also have modular exponentiation, which is used for fast calculations in cryptography. All right. So if there are any questions, as per usual, you can drop them down in the comments, and also you can text in the WhatsApp group, and I'll get to you as soon as possible. As for now, thank you so much, and take care. Enjoy your day.